right, we're back again. I'm just trying to make sure that you can actually see the ends of the board, because that would be bad if you can't. So, welcome back. Here we are where last time we were talking about slope fields for first order ODEs of the form y prime is some function of x and y, the independent variable and the dependent variable, right? The unknown function is y of x. And we said that in addition to like understanding the slope field pictures, for example, that are in the book for you, what you want to be, and the ones that you create with just the little slopes of tangent line hash marks, right, throughout the xy plane. In addition, what we want you to be able to do, what I want you to be able to do, is check that Picard's theorem hypothesis hold and figure out where that holds. So remember, what was that? It's that f and partial f, partial y are continuous, right? Okay, we'll do one of these calculations at the end of this video. Okay, then we want to look for equilibrium solutions. What are those? Y equals a constant, right? So that y prime is 0, right? Y equal a constant of giving y prime equals 0. Then you also want to determine where do solutions have horizontal tangents, right? So there might be other places where y prime is 0, right? Along which are not constant solutions. Y equal constant horizontal line, right? Horizontal lines are nice because they split the xy plane into separate little areas and regions, and because of Picard's theorem, if we have these two things being true, then you can never cross any solution, right? So these guys would split the solution. You couldn't cross the solution because that would be a place where you would have two solutions satisfying the same initial condition at the crossing point, right? So that's not possible if you've got these guys. So these are super nice in helping us understand where solutions can go in looking at these slope field type problems. So in addition, we want to figure out when solutions, across what types of curves do solutions cross with horizontal tangents, like in our last problem, where it was a line. Where are solutions increasing, right? So when is y prime positive, right? Reinforcing our calc. Where are solutions decreasing? So where is y prime negative, right? And then, provided it's reasonably simple, where are solutions concave up? So where is y double prime positive? And where are solutions concave down? So where is that y double prime negative, right? So let's just pick up with this guy. Maybe you tried it already. We said it has no equilibrium solutions, right? Okay, no equilibrium solutions. What is our f of x and y? Our f of x and y is x minus 2y, right? So what about Picard's theorem? Is this function continuous everywhere for all x and y? Absolutely, right? Nothing bad happens there, right? It's continuous for all x and for all y. There's nowhere that it's a problem. What about its partial derivative of f with respect to y, right? What does that mean? It just means pretend x is a constant and take the derivative with respect to y, okay? So if I pretend x is a constant, take the derivative with respect to y, then I get 0 from that derivative. And what is the derivative of minus 2y with respect to y? Good, it's minus 2, right? So the partial derivative of f with respect to y is negative 2. Negative 2 is a constant, and constants are continuous everywhere, right? So we have these nice, continuous, we have no problems anywhere that we need to worry about, right? Okay, so now let's go, we already did number 3 then, last time, where do solutions have horizontal tangents? So this is the line across which this solution had a horizontal tangent. So this solutions of this differential equation would have a horizontal tangent. So let's draw our xy plane. okay? Y equals 1/2 x, right? That's a line like this. So here's a graph of y equals 1/2 x, yeah? Okay, and maybe I'll just draw them in here in blue this time. So across, when a solution crosses this line, it has to cross with a horizontal tangent. So we have horizontal tangents, right, across this line. Does that make sense? That's the slope of a tangent line. Those are our horizontal lines, even though that one doesn't look so horizontal, right? Is that better? Okay. It's hard to just close up. Those are all horizontal lines. Wow. Yeah. Okay. Is that better? Oh my gosh, none of this look horizontal, right? It looks horizontal when I'm way up here, but it doesn't look horizontal there. Let's try that again. Okay. So I'm just gonna put in the slopes so that I don't forget. So across the line, y equals 1/2 x. Yeah, does that make sense now? Okay. The solutions cross with a 0 slope. Okay. So now let's look at what else we're going to do. So where are solutions increasing, right? Solutions of this guy would be increasing. So that's our question, right? Increasing. Y prime positive. What does that mean? X minus 2y is positive. What does that mean? X is greater than 2y, right? Which means y is less than 1/2 x, yeah? So solutions are increasing when y is less than 1/2 x, right? And where are solutions going to be decreasing? When y prime is negative, which is going to say that x is less than 2y, or y is greater than 1/2 x, right? And so over here, solutions are decreasing, and here solutions are increasing. Does that make sense? Okay. If we wanted to look at some specific values, right, we could do what we were doing with our table, right? So, but now we need an x and a y, right? Because what's our y prime? Our y prime is x minus 2y. Okay, so we have to pick an x and pick a y, right? Pick an x and pick a y. Like for example, if x is 0 and y is 1, if x is 0 and y is 1, what do we get? -2 is the slope. So if here is 1, our slope is -2. Yeah, does that make sense? Okay. If x is 0 and y is -2, right, then what do we have? Y prime is +4. Yes? So here's -2, our slope is +4. Yeah? Makes sense? That's -2, that's +4. So this gets a little bit harder when you don't have a nice little, computer program or graphing paper. But in this particular problem, which is 1.2.6, right, they give you the slope fields, but I want you to make sure that you understand where all of those little hash marks are coming from. There are all these little slopes, like by just evaluating, right? Does that make sense? Okay? So you can use that to help you determine which slope field goes with which differential equation. Another simple place is to go out here on the x-axis, right? So what if we have x at 1 and y at 0, right? If x is 1 and y is 0, then what do we have? A slope of 1, right? And so across here, right, at that spot, we're going to have a slope of 1. But unlike the previous problem, right, you can't just say, oh, that's the same thing no matter where you are, right? Because the slope is going to change with the x and the y, right? If x is 2 and y is 0, then the slope is 2, right? the slope of 1 and that's the slope of 2. Yes? Okay? So, let's jump over to the idea of concavity for this one, okay? So for this one, if we're going to think about concavity, y double prime, now we've got to be a little bit careful, right? So y double prime, here's y prime, okay? What is y double prime? We're taking, this prime means a derivative with respect to x, right? That's what we're doing, derivative with respect to x. And so what is the derivative of x? Good, 1, right? Minus 2 times what? Well, what's the derivative of y with respect to x? Very nice, y prime, yeah? Okay, so, well, what do we do with that? Oh, right, wait, y prime was this, so we plug it in there, right? So that's 1 minus 2 times x minus 2y, right? But that's 1 minus 2x plus 4y, right? So now we have an expression for y double prime, and if we set this guy equal to 0, that will give us a line along which concavity changes. So you can go ahead and do that for yourself. It's a little bit uglier than our other nice little line, but you should be able to see how concavity would change on either side of that line from this, okay? We're not gonna worry so much about that one because it's not a nice, reasonably simple concavity one to graph, but the next one, also in that same problem, that I want you to think about how you would deal with all of these pieces. Here's the last ODE in 1.2.6, I believe, was the exercise. I think so. Yes, exercise 1.2.6. That one is y prime is equal to x times 1 minus y, okay? And so for that one, see if you can walk through all of this in order to come up with a understanding of the slope fields and the direction fields, the increasing, decreasing, concave up, concave down, breaking up of the plane, the XY plane, based on calculus, okay? I'm gonna have you think about that. We may come back and do that one. I'm going to end this video with talking just a little bit about a couple of things to remember that might help when you're doing that, okay? But it's getting close to office hour time, so I'm gonna have to stop this video. So let's try to wrap something up, and maybe we'll come back and take a look at that guy after you've given it a shot. Yeah? Okay? So, with this. So, some other cleanup of section 1.2. That's kind of where we are right now. Okay? So, suppose we have this guy. This is our differential equation. So this is our f of x and y. right? Yeah? Okay, so when we look at this guy and we say, when is this continuous? This is continuous for what? What's the first problem that you see? Right, division by x, right? So we can't divide by 0. So this is continuous for x not equal to 0, right? And do we have any restrictions on y? Yeah, y has to be greater than or equal to 0. Yeah, does that make sense? Right? So this function is not continuous, so we put it a negative y, and not continuous when x is 0. So what do we have already? Here's the xy plane. X can't be 0, so you can never be on the y-axis, right? The y-axis, never, right? And y has to be greater than or equal to 0. So we either have to be in quadrant 1 or quadrant 2, or on the y equals 0, but not y and x equals 0. Yeah, does that make sense? Not including that guy, he's not allowed in. Yeah, okay, are we good? So these are the only places where that guy is continuous and makes any sense. So what if we take the partial derivative of f with respect to y then, right? Okay, well, how do I rewrite this so I can nicely take the partial derivative? Pretending x is a constant, well, y divided by x, if I leave it like that, I have to use the quotient rule, and I don't want to do that, right? Even if it's a constant. So I'll write it as 1 over x times y plus y to the 1/2, right? That's in, that f of x and y is in better shape for taking a derivative, yeah? Okay, with respect to y. Now we're going to pretend x is a constant, so if x is a constant, 1 over x is a constant, so this is just a constant times y. What's the derivative of constant times y with respect to y? Just the constant, right? Then we're going to take the partial derivative of f with respect to y, so we're taking the derivative of y to the 1/2 with respect to y. What is the derivative of y to the 1/2 with respect to y? 1/2 y to the minus 1/2. Yeah? Okay? Okay, so what do we have here? We've got 1 over x plus 1 over 2 times 1 over the square root of y. So this guy, right, we already ruled out x being 0 and x being negative, right? This partial derivative is not continuous at either of those guys either, but we also then have to say y can't equal 0, right? Plus, right? We have that guy, we have that restriction, plus y can't be 0. So that rules out this little line as well. Yeah? So you have to be legit in one of these two quadrants and not on the axis. Yeah? And not at the origin. That means you cannot get Picard's theorem will not guarantee you a unique solution if you have initial condition assigned at anywhere where you're violating the hypotheses, right? So in particular, you're only guaranteed unique solutions if you stay in this quadrant. Your initial value is some x not y not in here. Or if you stay in this quadrant, and you'll have a unique solution in here, right? One or the other. But if you venture outside into these realms where we don't have continuity, then all kinds of crazy things can happen, right? So for example, the initial value problem, that ODE, and y of 0 equals 0, right? That would be saying, okay, this point, this guy is on the curve, of the solution curve. That's one of our bad spots that's not allowed in, right? That initial value problem has infinitely many solutions. Okay? So crazy things can happen, right? Just by assigning this initial condition here, we get infinitely many solutions. Infinitely many curves go through this point that solve that equation. Whereas if we're up in here, it's gonna be a unique solution. Crazy. All right. Other things to keep in mind as you're doing these problems and trying to do them well is a couple of calculus things, okay? So here we took the partial derivative of f with respect to y, right? So if we write this, if we were just talking about the derivative with respect to y, right, of y to the 1/2, right, okay? That is 1/2 y to the minus 1/2, yes? But what if we're taking the derivative with respect to x of y to the 1/2? Well, here you've pretty much understood that y is this function of x, right? Okay, in our differential equation framework, right? This is the dependent variable. Y really means y is some function of this independent variable. And so if I'm going to take this derivative with respect to x of y to the 1/2, then what rule do I have to use from calculus? Chain rule, right? Yeah, so this is the derivative. This is the same as saying take the derivative with respect to x of y of x to the 1/2 power, right? What does the chain rule say that is? 1/2, right? Leave the stuff alone. Subtract 1 from the stuff. Multiply by the derivative of the stuff, right? Or in shorter notation, 1/2 y to the minus 1/2 times y prime, right? Okay? So you gotta be careful what you're doing with what you're taking derivatives with respect to. We're taking these partials, we're taking derivatives with respect to y, and therefore we're treating x like a constant and then just dealing with derivatives with respect to y. But if we're taking these derivatives associated with concavity, then we're taking derivatives with respect to x, and that derivative would pop us up an extra multiple of y prime because of the chain rule, right? In the same way, if I had an x times y, right? These were always your favorite things when you're learning. Like right in there was an x times y, right? Like what is the derivative with respect to x of x times y? What rule do you have to use? Right, product rule. Right, why? Because that guy is really a function of x. It's x times y of x that you're taking a derivative of. So that's a product rule, yeah? Okay, that's a little heads up to avoid possible problems. And I guess I'm just gonna close that up here where we are now and post maybe, well, I'll post these videos and maybe one more on this section.